Today we are going to talk about frames and machines. Okay, you might have a vague idea of what these things are, but today we are going to define it. We're going to see how to deal with this kind of thing, and we are at the stage where we have the capacity to solve much more complicated things which are actually fairly close to real life objects. Okay, so let's see if we can talk about a little bit about this. Here we go. Okay. Before we go, I want to iterate this throughout the semester. What are the steps in the analysis of a rigid body? So first thing is identify and isolate the body or system and draw its outline separately. This is the free body business, right? The second thing to do is at each point where it interacts with external bodies, idealize the interactions as force and or moment. Okay, so sometimes it is just one component of force, sometimes it's a distributed force, sometimes you have to put distributed force and moment, you have to make a decision. Okay, convert the picture into a vectorial representation. This is where you have to use a combination of your trigonometric and vector algebra skills. Use the laws of mechanics to set up the equations. This is very straightforward. This is, in our case, this is fairly simple because we are going to do only statics, which means that sum of all the forces and sum of all the torques must be equal to 0 for every rigid body. So this is something that we will think about a little bit as we go along. Okay, count the unknown components and equations. So it's not automatic that just because you set up the equations there are enough equations to solve, or there are enough unknowns to solve. So you have to count and make sure that you have enough equations for unknowns. The typical scenario is that you will have fewer equations than unknowns and you will have to augment them. Augmentation is based on empirical laws. Hooke's law, Coulomb's law of friction, electrostatics, gravity, all of these things are examples of additional laws that we add. These are not really laws, these are assumptions, empirical equations. Okay, we have to do this, there is no other way. And this item 5 requires some serious judgment. Last thing is, we got to solve the resulting set of equations and verify the reasonableness of the solution. So items 1 through 6 are what we need to do to analyze it. Item 7 is what you do with the result. You have to use the result to make engineering decisions, and usually you don't need very accurate results to make engineering decisions unless it's a very special case. Okay, this 7-step deal is what we have been talking about for quite a while. Now we are going to apply it to real world rigid bodies. So real world rigid bodies come in two kinds. Something which is called a frame. I mean, this is a broad classification. Of course, don't tell me, hey, it said only two kinds, but I found a third one. I'm not really talking about big brush here. So we're going to do a broad brush. First one is what is called a frame. The second one is what's called a machine. So before I talk to you about frames and machines, please think about and write down a few items as to what you think a frame is and what you think a machine is. Okay, so pause it, do that, and come back. Did you pause it? Did you do that? Did you come back? Very good. So let's see. Frame. So I've shown you two kinds of things. One is actually this gigantic object that is used to transport very large things into the ocean. The other one is actually the new bridge that was built across the Hoover Dam, and it's being built. You can see the arch coming out, and there are cables that are attached and so on. These two are examples of frames, and a frame is bodies joined together in order to sustain forces and moments with minimal deflection. So in this particular case, this object is able to sustain the force generated by the force of gravity onto this object, and it is able to do that with minimal deflection. So you don't want to build it out of rubber, even if rubber could take the load, because it will sink this whole thing. Okay, it's primarily used for locating or constraining objects. So the primary purpose of a frame is to locate other objects, to make sure that they are in their proper place. And as a result of this locating constraining effect, there will be constraint loads, and the purpose of a frame is to transmit this constraint loads to the ground. So it has two things. One is locating objects, second thing is transmitting the force to the ground. That's what we mean by a frame. Machines or mechanisms are bodies connected together in such a way that an input load or motion is transformed into a possibly different output load or motion. Usually these are pretty nice. So I'll show you a couple of different mechanisms. The first one is, notice, watch this for a second. Okay, so you watch this now. Tell me, just think about it and tell me what is the input motion and what's the output motion. Okay, so pause, think about it, write it down, then I'll tell you what it is. Did you pause? Did you think about it and write it down? Look, just watching me doesn't give you a whole lot. Okay, you might say, fine, you know, I've finished watching the video, but it's not going to help you much. You have to do. Okay, so follow with me. So what happens now is the following. Notice that the input is here, the crank, and you can see that the crank just goes round and round. Okay, oops, excuse me. Okay, the crank just goes round and round, that's all it does. But look at the output. Can you see for a while it has stopped? Now it goes back up again. So it oscillates back and forth, but with a dwell. It stays for a while. So now it took the input motion, which was a steady rotation, and transformed it into arch. So back and forth motion, but with a dwell. This is needed in many cases. Here's another example. This is a box transport mechanism. You will see how this one works. These red boxes, these reds are the boxes, and this is the input motion. Can you see the input motion is round and round? Look at the output motion. It's going down, but with a particular amount of time lag. Can you see that? And you can see how cleverly this is done, so that a fairly complex thing, all the boxes are moved by the same amount, as we go along. Right? Both of them look like two-dimensional mechanisms, but in reality there are no two-dimensional mechanisms, there are only three dimensions. So now I am going to show you some examples in the agricultural sector where mechanisms are very widely used. In the first one, I am going to show you a rice tilling machine. Oops, sorry. Can you see that? It cranks. And you can see the complicated mechanism there. The next one I'm going to show is a leek punching and planting machine that will till 3,500 plants. This is an actual one. You can see that there's some mechanism inside a cage, and in this particular case I want you to notice that there is both a structure or a frame, that's the outside thing, and a mechanism inside it. The frame is there to locate this thing, and you'll see very soon how it's planting. Can you see that? This thing drills the hole, that thing plants the leeks. Right there, it's planted. That's how it works. Okay, and I want you to understand that many of these mechanisms, in this particular case I'll show you how the leeks are fed into this device. So there's a big drum there, the drum is rotating, so you put the leek one at a time into the drum. Can you see that? And then it gets planted. And there's all kinds of devices to monitor this thing. There's a little encoder which tells you how far you've moved and all this stuff. Okay, so I hope you got the idea of what is meant by a frame and a machine. So next item, we are going to look at how to analyze these kinds of things when they are moving very slowly, that is in a static, by using only statics.